Now I'd like to ask if Jake Lang is in the house somewhere. Yes, here he is. Fantastic. So Jake is an Ethereum core developer at the Ethereum Foundation, and he's going to speak to us about Ethereum WebAssembly, the future of smart contracts. Thank you, Jake.
Hello everyone, I'm Jake Lang. I'm an Ethereum core developer working on the ETHIS team. And so, in a departure from the crazy world of consensus protocol design and Ethereum research, I'm going to be talking about the future of the EVM in Ethereum and why it isn't the EVM. In the past year or so, the ETHIS team has been working on a complete redesign of the Ethereum execution layer using the new WebAssembly instruction set architecture. So, in order to understand why we need to switch to WebAssembly, we still need to look at the fundamental flaws of the EVM's design. So these can be boiled down to a few basic points. The first being that, well, it's complicated. So the current EVM's design mixes high-level opcodes for cryptographic primitives like catch-ack and other high-level functions with basic logic and arithmetic opcodes. And as a result, you have a VM that's not really performant at all. There's a lot of software overhead for translating the 256-bit arithmetic operations into operations that your computer's processor can actually understand, which slows down the blockchain by a significant amount. And so, well, the other thing is that all of the work on the EVM is done, well, not just the EVM, but all the tools, libraries, and languages surrounding it are done by mostly either the EF, Consensus, or a couple other groups that work on such tools. So here we have a very long list of languages used in production targeting the EVM. As you can see, it's actually not long. And that's kind of the problem with the current developer ecosystem targeting the EVM. It's inherently centralized to the people that actually work on Ethereum. And so, enter WebAssembly. So, WebAssembly is essentially a VM specification and instruction set architecture initially designed for the web. But it also finds its place in embedded and portable environments that require an execution engine that's deterministic and simple. So, especially in our case, that's extremely useful because WebAssembly is simple, modern, and fast, which makes it well suited to computation in a blockchain context. So, one of the main benefits of WebAssembly is obviously its performance due to its minimalistic design. So unlike the EVM, which has 256-bit integers by default, WebAssembly is much more similar to the processor in your computer, a 64-bit or 32-bit processor running either ARM architecture x86, and the address space is, 64 or 32 bits, just like WebAssembly, which lowers the overhead for translating the operations that WebAssembly code carries out into code that your processor actually uses. So you can go about this two ways. You could build an interpreter, which essentially acts as a runtime environment for the WebAssembly module, and that's what we use at the moment in our existing WebAssembly VM Hero. But there's also a just-in-time compiler, which is a compiler that also executes the code generated on the fly. Now this is very significant because of the performance benefits, but the security risks are also an area of active research right now. And so, the most important part of adopting WebAssembly, in my opinion, is actually the benefit you gain from the vast developer ecosystem of tools and languages surrounding the WebAssembly VM specification. So, to demonstrate the degree of language support that we get from adopting WebAssembly, the following, okay, so actually, well, we should probably cover what's the difference between Ethereum WebAssembly and WebAssembly. Well, EWASM is WASM, except for the fact that we reject any WebAssembly code containing sources of non-determinism at the contract deployment time, like floating point operations. For example, a part of the WebAssembly spec actually does have a source of non-determinism. That's floating point. We reject that before a contract is created that can potentially introduce undefined behavior in the WebAssembly module running on the chain. So, as I was saying earlier, to demonstrate the degree of language support we get from adopting WebAssembly, here's a small diagram of the LLVM compiler infrastructure. So, for starters, we have C, C++, and Rust sources, which are all traditional systems programming languages that usually are targeting native. But they can also be used leveraging LLVM to target WebAssembly and are especially useful for generating optimized code for smart contracts that require intensive computation. Now, because of LLVM's modular architecture, the WASM backend generating the WebAssembly bytecode is actually completely decoupled from the rest of the infrastructure. So for any language for which there exists an LLVM front end that generates the LLVM intermediate representation, it is also theoretically possible to use the said language to generate WebAssembly bytecode for use in Ethereum WebAssembly contracts. But what if, nobody really wants to use C, C++, Rust, nobody wants to mess with dangling pointers and memory leaks and condemn themselves to a hell of just nullity references, use after free bugs that essentially suck up your time trying to fix something that should work off the bat. So for that, we actually have an alternative language that the EWASM team intends to use as the primary contract language for EWASM. Assembly script. Now, assembly script is a subset of TypeScript, which is in turn a superset of JavaScript. So, as you might expect, it will be similarly easy to use, kind of like Solidity is at the moment, hopefully. And that will hopefully lower the gap of jumping from working on native stuff and web development to working on smart contract code. Now, because assembly script is super easy to use and expressive and brief, the EWASM team intends this to be used as the main contract language for EWASM, because most people will not take much time to pick it up. So, to take a look at how similar a Solidity workflow and source code is to assembly script, let's compare some basic token contracts in both Solidity and assembly script. So, the first one is Solidity contract. This is a basic token containing a subset of all the methods defined in the ERC20 standard. You have, well, it's borrowed from the ETHIS website. Has a transfer method and an initializer method. And, well, anybody coming from the world of JS or any other language with similar imperative design will probably be able to understand this relatively quickly. Now, let's take a look at assembly script now. As you can see, assembly script is very, very similar. It includes both the imperative and object-oriented features that Solidity also has, well, along with most languages. And as you can see, in the same number of lines of code, you can also express two more of the standard ERC20 methods, which is a good demonstration of, well, how easy it is to use languages that exist for WASM, which is still relatively new, but actually has a surprisingly developed tool chain. So, some of you might be wondering, would it make sense to actually throw away all the EVM work that has been done in the past years, all the languages, IDs, and libraries that have been developed in order to make EVM working with EVM not a pain, supposedly. But the EWASM team has actually devised a variety of measures to ensure that EWASM is sufficiently backwards compatible that anyone writing in a language for EVM could actually still develop for an EWASM-based chain. So the first of these is RoomVM, which is essentially Parity's EVM interpreter ripped out of Parity and turned into a WebAssembly system contract that can be used on the chain. So for example, a Solidity developer working on the EWASM chain can compile their Solidity to EVM and deploy it like a normal contract. But instead of being executed in WebAssembly, it will be executed by an EVM interpreter compiled to WebAssembly. Now, the next measure that we have planned is compiler support in Solidity. So Solidity has an experimental IR called Yule, and Yule is essentially basically a simple AST-based format for modularizing a compiler. So at the moment we have a WebAssembly backend for Yule. That means that Yule can actually generate WebAssembly. See, the missing part is actually that we're missing Solidity to Yule, which is a problem. But that's planned. Don't worry about that. Now, the last and most mature option we have for backwards compatibility is EVM to WebAssembly transcompilation. So we have the first one, which is much more mature and developed, is EVM to WASM. There's a C++ port of the initial JS version, and it's essentially a one-to-one translator of EVM opcodes to WebAssembly, as the name might suggest. The other option actually is YEVM. This is interesting because it's actually a decompiler from EVM to Yule. So a Solidity developer can generate WebAssembly from Solidity by compiling their Solidity source to EVM, decompile it using YEVM to Yule, and then leverage the Yule backend to generate WebAssembly. Now, of course, that's complicated, but that's why we have a large variety of tools that we can choose from for ensuring that we can still leverage the existing work done on EVM. Now, let's take a look at what we did in the past year or so. So, we have an EWASM VM implementation that supports CPP Ethereum and Geth, actually, ERA. And more recently, work has been done on it to abstract the entire VM so that it can support the majority of existing WebAssembly execution engines, JITs, interpreters out there. And we're slowly working on introducing support for another interpreter and a JIT compiler that promises to potentially improve contract execution time for your average contract to the microsecond level, close to nearly 5 times. And additionally, on the DevX side of things, we have developed user libraries for common languages targeting WebAssembly, including C, C++, Rust, and, well, more importantly, assembly scripts. And the important thing, more recently, is we have an internal testnet now as an Explorer, a faucet, and, well, working contracts and networking. And for those of you that are so eager to try out all the cool stuff we've been working on here at the EWASM team, we have a public testnet planned for release before DevCon. Additionally, we'll also have a workshop at DevCon where you can try out all the stuff with the assistance of the EWASM team. But you also don't have to wait for the EWASM public testnet to arrive. We have documented the process of setting up an EWASM node on either Geth or Alex/CPP Ethereum so that you can try out all of the stuff we've been working on your own before the testnet arrives. Now, here's the question of the year. How do we actually deploy Ethereum WebAssembly? Now, the first one is pretty obvious, even though it's kind of complicated. It's, Ethereum 2.0. EWASM will potentially be the main execution engine for Ethereum 2.0, unless there's another execution engine that comes up and is much better than EWASM. And so for us, that really only needs us to redesign the host interface for execution and sharding content. And, well, yeah, that's how EWASM will be a part of Ethereum 2.0. But what about the case that Ethereum 2.0 takes longer than it should, and we're kind of blocked on deploying EWASM, and we don't want to wait 2 years to introduce improvements that might be needed? Well, we have a multi-stage approach to introducing WebAssembly on the mainnet. First, as precompiles, which can have the potential to streamline the precompile development and testing process because of WebAssembly being a simple and deterministic substrate for developing such precompiles. And the second stage is obviously as contracts. The backwards compatibility initiative is still a big part of this, and we have to significantly develop that effort in order to reach this stage. But hopefully Jasper will come soon, and we'll be able to introduce WebAssembly in that time and achieve that utopian Ethereum 2.0 that we've all been working for so long. And so, thank you for listening. If you guys are interested in potentially trying out EWASM in its current stage, or even contributing to it, then we're on Gitter. You could join our channel and get in contact with us, and we could exchange notes or share questions, and potentially even get some more contributors working on the EWASM toolchain. So yeah, thanks for listening, guys.
Thank you so much. Excellent. So we've got one more